Okay, so the ionic compounds had those crystalline shapes. Covalent compounds can have very, very different shapes. Not everything's at 90 degrees, and it all depends on how they are bonded together, right? Because like carbon monoxide has a different shape than carbon dioxide. So, review here. What do molecules, covalent compounds, do with their electrons? Do they share or do they transfer them? I hope you said share. All right, so that sharing can happen unevenly. All right, there can be one atom that hogs the electrons versus the other atoms. And that ties into electronegativity. All right? If you were to combine fluorine and hydrogen, right, they have huge differences in their electronegativity. That fluorine is going to hog that electron that hydrogen provides. All right, it's not going to share that evenly. Whereas if you combine hydrogen and carbon, carbon really doesn't have that much stronger of an electronegativity than hydrogen. They're going to share their electrons fairly evenly. All right, so you run into polar compounds when there is a difference of greater than 0.5. All right, so using that rule, if the electronegativity difference is 0.5 or less, it's nonpolar. But if it's greater than 0.5, then we call it polar. See if you can identify which molecules here would be polar. So to do this, you look at, so like N2. It's a nitrogen paired with a nitrogen. So they both have an electronegativity of 3.0. That would be nonpolar. Right? In fact, anytime you run into those diatomic molecules, they're nonpolar because it's two of the same thing. They're going to have equal polarities. Of the rest that are left, we've got NCl3, which is 3.0 and 3.0. That's going to be nonpolar. I'm going to pause it here, see if you can figure out which ones of these are the polar ones. All right, so we've got H2O, which is 2.1 and 3.5. Oh yeah. And that polarity is what gives water a lot of its important properties. Hydrogen, fluorine. Oh yeah, that's the biggest. Fluorine almost always makes polar molecules. The only one it doesn't do that with is oxygen. And then CH4 is 2.5 and 2.1. Nope, nonpolar. So, see if you can answer this question. What best explains why methane, CH4, is not a polar molecule? If you said B, you are exactly right. All right, that's what determines whether or not you've got a polar molecule, is that difference in electronegativity. The rest of this doesn't matter. All right, so this polarity thing factors into valence shell electron pair repulsion. So, Vesper, oh, I spelled it wrong. This should be Vesper, is the model that chemists use to determine the shape of a molecule. All right, and this theory, which is backed up by lots of evidence, makes sense if you think about the molecules spreading out their paired electrons as much as possible. Like those electrons, they're all negative, they repel each other. So the shapes are determined by, what shape can we get all of our electrons to be as far away from each other as possible. All right, and the electrons you have to worry about are going to be your electrons that are in bonds, right? So those shared pairs, as well as you'll have certain atoms that maybe have a lone pair of electrons that aren't involved in bonding, all right? So like these two molecules both have 4 positions where electrons exist that are going to try to repel each other. But because one of them has a lone pair, that will result in a slightly different shape. So, these two that we talked about. So when you have a molecule that has 4 bond locations, all right, and there's no lone pairs, anything like that, you get this shape of being tetrahedral. All right, so, and these are actually all 109.5 degrees apart, and that's the maximum you could get all of these electron areas away from each other. So you got one going straight up, and then it kind of pushes down the other ones. Ammonia, the NH3, has 3 bond locations and a lone pair. Its shape is what we call pyramidal or trigonal pyramid. All right, it's essentially the same thing as the methane. It's just there's nothing but electrons up here. So it's kind of like the bottom of the tetrahedron. So these are names that you want to write down. All right, you might even want to write down the examples. Because questions you're going to have in is like, which compound has a pyramidal shape? It's going to be, something with 3 bonds and a lone pair. Other shapes you want to be familiar with is water. All right, so water has, 2 lone pairs that we don't see in the shape because it's electrons. And then the hydrogens are pushed down, so it has this bent shape. And that's how water gets its, positive bottom area and negative top area. All right, and then there's a lot of examples that can give you a linear shape. All right, your diatomic molecules, so Cl2, O2, H2, you just have 2 things bonded together, that's going to give you a linear shape. If you have carbon double bonded to 2 different chemicals, you'll get a linear shape. Or if you have carbon with a triple bond, that'll get you a linear shape. All right, so 2 double bonds or a triple and a single bond on carbon will also get you a linear shape. All right, so again, these are things where, you're just gonna have to take notes here, have this stuff handy so that you can answer the questions when it asks you, which molecule would have a linear shape. So, which compound would likely have a bent triatomic structure? All right, so bent is like this. All right, there's also the triatomic. Should sit there and be like, oh yeah, you know what? There should be 3 atoms in this. So there's a few ways you can kind of narrow this down. All right. 1, it's triatomic. There's only one choice here that has 3 atoms. All right. And while there's some bending to these other structures, these 2 would have pyramid and tetrahedron sort of stuff. This only has 2. So this is H2S, which has a very similar shape to water.